All right, it's a pleasure to have Malik Hassanaly, National Renewable Energy Lab. He's a research scientist there, and he will talk today about generative modeling and scientific sampling to us today. Before joining NREL, he was a PhD student at the University of cGAN, received his PhD in 2019. And before, he was a master's student at UT Austin. His research interests include design optimizations, and he's done fantastic work in the field of data-driven modeling with applications to uncertainty quantification, learning, and reduced order modeling. And he's been awarded the Richard and Eleanor Towner Prize for distinguished academic achievements for his work in this area. So with no further ado, Malik, I turn it to you. Floor is yours.
Cool. Thanks a lot, Mohammed. Yeah, let me know if you cannot hear you can hear something weird. But otherwise, yeah, if you have any question, you can stop me during the presentation anytime. And Mohammed, I'll let you just interrupt me whenever this happens. Okay, so I work at the National Renewable Energy Laboratory, and my background is in fluid dynamics and in turbulent combustion modeling, as Mohammed hinted at. But recently, I've been looking at data-driven models to process the amount of data that we're generating, in particular into generative models for scientific sampling. And so there's a bunch of applications that come from there, which I'm trying to make you think that this may be useful for your own applications. That's my goal today, to show you that. Okay. So before I start, let me just give a quick definition of what generative models are. So given a data set x1 to x2 to xn, a generative model is going to be tasked with generating data that could have been in the data set. So said differently, the generative model is going to draw a sample of a distribution that is defined from a given data set. And this has application for a variety of topics. For example, for data alteration, well, let's say you have a classification task, but you have an underrepresented class, and you may want to rebalance the data set by generating data on the underrepresented class. Or for denoising, where you want to, for example, generate data at a higher resolution or generate missing data. So it can be also useful for time series prediction, where you generate data in the future, or for as design assistant in the industry, getting a lot of traction right now, to generate possible design that meets some engineering requirements. And so what I want to tell you today is that these generative models are nothing else than sampling tools, where we can draw sample at high quality from high dimensional distribution with relatively small support. And the sampling problem, they do happen quite a lot in many areas of science. So I'll focus on two different topics today that are actually completely opposites, but that really show the breadth of application that come from them. So the first one is data augmentation, which in a sense is state estimation for atmospheric fields. So we're going to generate high-resolution data from low-resolution inputs. And the second application is exactly the opposite, where instead of doing data augmentation, we're doing data reduction. And we're using the ability of a generative model to estimate efficiently high-dimensional distribution, high-dimensional PDFs to do that task. Okay, so throughout the talk, you'll see this QR codes. This is, I thought that if you wanted to use your phone and just grab the paper like that, you can do this. So for both of these applications, we have paper and we have a code, and you're welcome to just look at it, and we can discuss about this after that. Okay, so we're going to start with the state estimation for atmospheric field. So the problem that motivates all of this is the coarse availability of data, the sparse availability of atmospheric data, in particular of wind data. So typically, when you collect wind data, you use what we call Met towers. So this is what is shown on the top left, and you have these Met towers scattered around fields. So typically, every tens of kilometers, you may have one. And on this Met tower, you can measure the temperature, the pressure, and the wind velocity just at the location of the Met tower. So you have a very coarse description of a wind field using that. Alternatively, you can use global atmospheric model outputs. And so there's people who run routinely global atmospheric models which gives you wind field data at, let's say, the kilometer scale. But really, for many applications that involve winds, we may be interested into much higher resolution data about the wind fields. For example, if you want to do resource assessment at a wind plant level and decide which wind turbine should be decommissioned, which wind turbine should be maintained, where we should put more wind turbine, you need wind information at the wind turbine level, not at the tens of kilometers scale. If you're on a plant actuation policy, a very popular way of actuating wind turbine is to do wake steering. So you can take an upstream turbine and orient the wind so you steer the wake so that you increase the energy that goes into the downstream turbine. You need to have a good understanding of what is the interaction between two different wind turbines. And again, you need more than kilometer scale resolution. And finally, if you want to enable high fidelity simulation, now you need initial condition at a much smaller scale than the wind turbine. And so the task we have here is to increase the resolution of the wind fields using low resolution inputs. So this is nothing else than a super resolution problem, and there is a bunch of methods we can use for that. But the trick here, and that's a very important aspect for us, is that we are going to make costly decisions using the super resolve field. We are not going to, we are going to, for example, make financially impactful decisions or impactful for society. So here, uncertainty does matter quite a lot. In particular, the uncertainty I'm interested in is the coarse-graining uncertainty. So if you don't know what coarse-graining uncertainty is, I have on the right a picture of that I took from a turbulent flow book. And you can imagine that you may want to be able to estimate the dashed solid line, but you only have access to the value at the blue data points. And so in the end, what you want to do is to reconstruct the small scale of your function using large scale information. And this is a one-to-many problem. So you can generate multiple functions from these few data points. And ideally, what you want to do is to reconstruct all the possible functions from there.
Excuse me, Malik, this is Ilse. I have a very stupid question. Isn't the commonsensical thing garbage in, garbage out? So if garbage is low resolution data, then how do you manufacture from that high resolution data, just at an intuitive level?
So that's an interesting point of view. So it's kind of related to how much information you give in and how much information you give out. We don't want to give more information out. But by definition, we're increasing the resolution. So we're going to increase information. But essentially, we're going to balance this information gap using uncertainty. So if you're not sure about the high resolution, then you sort of conserve information.
Okay, thanks.
Yeah, so that's the idea of why coarse-graining uncertainty does matter. And so what we're going to do now is to use this wind fields that you see as this contour there. So those are velocity field in the easterly direction, so from the left to the right. And we have low resolution input, and we want to be reconstructing multiple high resolution fields. And you can see that they're all consistent with the low resolution input, but they do have some variation. That's where we're going to go. Okay, so the strategy we're going to be using is conditional generative adversarial nets. So it's a database model. We're going to show many low resolution and high resolution pair of data. And we're going to teach our model to generate high resolution using the low resolution input. So a generative adversarial network, if you don't know what that is, it works with two different neural networks that are going to compete against one another. First, you have a generator that is going to generate the high resolution data, and that takes as an input the low resolution input. On top of that, it's going to take this z variable, which is a random vector. And the reason why we have z variable is because if you change the z variable a little bit for the same low resolution input, you want to force the generator to generate something different at the output. So that's the coarse-graining uncertainty. And the second one is we have a discriminator that is going to look at the generated data and the true data and figure out which one's true, which one's fake. And it's going to output the probability of this one's true, this one's fake. And the goal of the generator is to fool the discriminator. The role of the discriminator is to read through the generator. Okay, so this approach works. Many people have been using this, but it has a fundamental problem. So if I focus just on the generator and we look at how it interacts with its environment, it has a generator adversarial loss. So that's how much it fools the discriminator, and a content loss, which is how consistent is the high resolution with the low resolution. Let's say that for a given Z value, you generate a very good high resolution field. Now you have one good candidate for the high resolution, but you ask, what are the other possible high resolution fields? So you change the Z value and you expect a different output. But from the generator point of view, generating the same output for different Z value is the perfect solution because it will still minimize both of these losses. So in a sense, the generator is going to naturally ignore the Z input and not generate any coarse graining uncertainty. So that problem is called mode collapse. Many people have observed this before. And the way to combat it is to add another regularization, so another constraint that forces the generator to look at this random variable. So the way we're going to do this is we're going to use what we call mini-batch discrimination. So we're going to sample a bunch of this Z value at training time and generate multiple high-resolution inputs for each low-resolution input, and then look at the distribution that we're sampling. And then we're going to compare that distribution with a priori distribution we desire to sample. So the way we're going to do this is that we're going to just compute the first and the second order moments of the high resolution field we're sampling and compare it to the first and second order moments of the true distribution we would like to sample. Okay, so now the problem changed. How do we estimate a priori what is the distribution we would like to sample? So the way we characterize the distribution is with its moments. So what we need to estimate are conditional moments of this distribution. And this is not an easy problem here because we don't have categorical data. We don't, for each low resolution input, we have at most one high resolution output. So we cannot just do an empirical mean and an empirical standard deviation. We have to do something a bit more continuous. And so what we're going to do is to use optimal estimators. So if you think of two random variables, x and y, let's say they are 1D for now, and you find a function f that minimizes f of x minus y, the L2 norm of this thing. If you find that function is nothing else than the conditional estimator of y given x, which is the conditional moment of y given x. You can play the same game and construct estimator for y to the power p given x. So now you have higher order moment of y. And the problem here is to find that function f. But there is actually different, very good method to do this. For example, f can be a neural net. You can train a neural net that learns x, that takes x as an input and gives you y. And to make sure that you have the optimal estimator, you'd be increasing that the complexity of your neural net until you reach some sort of plateau for the mean square loss. And at that point, you declare, I found the conditional estimator, the optimal estimator.
To clarify what you mean by increasing the complexity of the neural net, the number of hidden nodes, is that what you're referring to? Right.
So you want to increase the number of parameters. So you can increase the number of layers, the number of neurons. Typically, in convolutional neural net, which is what we're using, one issue we have is that when you increase the number of layers, you don't have that much of an improvement at some point. So many people have observed that. So one cure that people use is to use what they call residual block, where you learn the outputs, and then the next layer is going to be learning the discrepancy of that output with respect to the true value. And by doing this, by increasing the number of layers, you do get a nice increase in the performance of the network. So that's what we did here. So we increase the number of layers until we reach some sort of plateau for the loss.
Okay, thanks.
Yeah. You don't have to use a neural net. You can use, for example, polynomials. You can do, and we actually do show that in the paper. And the interesting aspect is that this polynomials method to estimate conditional average, this has had some application in combustion as well. So in combustion, one thing we like to do is to characterize physics quantity in terms of fictional manifold variables. And these manifold variables are usually fewer than the physical quantities. We have fewer of them. And then what we need to have is the conditional value of this physical quantity with respect to this manifold variable. So this conditional average computation actually has some application in combustion, and we did use their method as well. And we do get good performance, better than state of the art, but not as good as using an NREL. Okay, so you can go the next step and extend that to vectors. You just have to be a bit careful, because when you have a vector and you compute a standard variance, you actually have to compute a covariance matrix. So here, what we did is a very harsh simplification where we approximate this covariance matrix with the diagonal portion only. So really, what you would like to be doing is a block diagonal approximation, but even then, with just the diagonal approximation, it was sufficient to get much better performance than before. The other aspect of this is that we are relying on the adversarial loss to give us information about the relation between neighboring data points. And so in a sense, we do have some constraint about the spatial variation. So we have some block diagonal information essentially from the adversarial loss that we do have from the, even if we are using a diagonal matrix. Okay, and so just to reiterate, the way this works is that you have your GAN, and on top of that, you have an estimator that estimates the a priori moment of the data you're going to be generating. And in the GAN, when you train it, you're using an additional regularization loss, which is the diversity loss, which is shown on the bottom right. And it's nothing else than a comparison of moments. We just compare the first moment and the second moment. So this is a Frechet distance here, but yeah, it could be anything. The E batch is the empirical moment. It's what we observe by sampling multiple times the GAN. And the E is just the a priori moment we compute. Okay, and so before I move on, this way of,
excuse me, I'm sorry, that divergence, that you can't compute that, right? That's just a theoretical thing.
So you can compute this. The E batch. So you
have the E batch, but you have the E.
Yeah. So the E is computed by using an external estimator. So you first compute for each snapshot your conditional moments, and then at training time you use that information to formulate that diversity loss.
Oh, okay. Oh. So yeah, okay, fine. Sorry. All right.
So there's this two-step going on. Yeah.
Yeah. Okay. Thank you.
And so before I move on to the training result and what happens, this problem of assessing diversity of the sample generated by generative models is a big problem in for many applications. We don't have a good way of doing it. And this was actually the first motivation of doing this work. But in fact, we can do, as you said, we can actually use this and then do the training using that information, and that encourage the diversity in the output. Okay, so the data set we're going to be using is wind data that is collected from numerical simulation over 6 years of numerical simulations. And we artificially coarsen it to mimic that super resolution problem. So in the paper, we have these two velocity components that are treated and evaluated a bit separately. But so this is the x velocity and the y velocity. Here, I just look at the x velocity because there's not much to learn from the other one as well. And so this is taken over the continental United States at many different locations. So we have 100 kilometer by 100 kilometer. Okay, and so I think before we look at the results, it's interesting to just look at the a priori moments. So at that point, we have not trained any GAN. We just look at a priori, what are the moments associated to the corresponding uncertainty. So this is an example on the left of a low resolution input and the true high resolution, the ground truth. And you can compute the first moment and the second moment of the subgrid scale quantities. So the first moment doesn't tell you much, but you can see that there is the filter. You can see the filter very clearly. For the second moment, it's a bit more interesting. So the second moment tells you where variation should happen at the small scale. And you can see that where you have most variation is in a region where you have the most gradients. And in particular, this location has a much larger second moment value. And this location here, what's going on is that you have a shear layer. You have a large gradient, large-scale gradient that is generating a lot of small scale. So that totally makes sense. This is where turbulence is the most intense in this field. And this is where you have a large uncertainty about the small scales. Okay, so the way we evaluate we train the model. There's different ways to avoid issues when you train the model. I'm not going to go in this, but we can talk about this if you're interested. But we can look at the results that we're generating. So we can assess the quality and the diversity, which are different things. The sample quality is how reasonable are the field we're generating. So we can look at different metrics. For example, the turbulent energy spectrum, which is shown on the top left. The black line is the turbulent energy spectrum of the high resolution field, and you cannot see it because it's behind the GAN-based method output. So they are very much on top of each other. And to put things in perspective, when we do turbulent flow modeling, we have some methods to do this task of super resolution. We actually call that deconvolution. So we have approximate deconvolution methods or Taylor expansion methods to approximate the inverse of the filter. And those things actually do inject some energy at a small scale, but usually it's not as much as it should be. And so it tends to smear out some gradients. You can do the same analysis with the PDF of the velocity gradient, and you do see something similar. So the ADM and Taylor expansion, they tend to underrepresent the large gradients. And the GAN and the high resolution output are very much on top of each other. And finally, for the sample diversity, there is different metrics we can use. We have them in the paper, but I think here it's much more interesting to just look at what we're generating and see if it passes your eye test. So this is on the left, you have the low resolution input. On the extreme right, you have the true high resolution output. And the conditional GAN output are in the middle. And you can see that we generate quite diverse set of outputs. And the diversity mostly is located in region where you have gradient in the low resolution value, the low resolution input velocity, which is consistent with what we saw earlier. Okay, so where do we go from there? So I think one immediate application, and this is where this method would really shine, is for remote sensing. So in particular, what we did look at is how do we apply this for mean sea level estimation. So sea level typically is measured with different methods, tide gauges, which are point locations, or satellite altimetry, which is very good in the open ocean, but very bad near the coast. And so you can actually use this to, in combination with like numerical simulation of mean sea level, to reconstruct what the mean sea level is near the coast. And so this method would really shine there because we have very small amount of data. And so the corresponding uncertainty is probably extremely large. For visualization, this can be useful. In my turbulent combustion background, that leads me to realize that when we do experiments and we want to measure stuff about combustion, we usually measure velocity and then maybe species mass fraction and temperature. And typically, velocity is very easy to measure, but species mass fraction and temperature may not be. And so you can imagine that you can generate the fields that are difficult to measure using the ones that are easy to measure. Another topic where we are using this for NREL mission space in particular is probabilistic forecasting. So you can imagine that you can generate future fields. That requires some model adaptation here, but you can try to generate multiple fields from present field, and you can try to generate multiple possible outputs. And that allows you to do something like stochastic estimation to figure out how you should react to a certain event. So for example, if you have a fire front that is propagating, you can figure out where it's going to go in the future and make multiple scenarios, and then decide what is the best course of action to protect the power grid or protect some community. And the last application that I've been working on a lot is also, it's quite surprising. It's for rare event probability estimation. So in rare event probability estimation, where the business there is to essentially reduce the variance of the low probability estimator. And to do this, you want to observe many more low probability events than what you would normally do. So there's different ways of doing this, but one of the way is actually to select events depending on how likely they are to lead to a rare event. Select a realization depending on how likely they are to lead to other rare events. And that selection step actually sometimes requires you to generate initial conditions for your system, which may be high dimensional. And those initial conditions, if they are not realistic and have the correct variation, you're not going to see the expected variance reduction. So this is the object of another paper. And if you want, we can talk about this later. But those are the type of application that I'm trying to show you where this thing can be used.
Malik, just to clarify or make sure that I understand, the samples you draw that would lead to rare events are from what you've not necessarily the low resolution.
Yeah, so essentially, yeah, so this can be low resolution that so in that case, what I'm showing here, the input variable would be the observable of your system. So typically it would be some quantity of interest that is lower dimensional than the system that you're looking at. And so you're selecting your events based on that observable. And so when you're selecting this system, you're eliminating some other, and you're replicating some of the events that are going to be headed to other events. And that replication step, that's a generation step. You're going to need to generate multiple initial conditions that correspond to that observable. And this is where this method can shine, where you have to generate a diverse set of initial conditions to then continue your selection step and go toward your events.
Right, right. Mm-hmm.
Yeah, I think it's, yeah, if you have other question, I would stop on this topic to then move on to the second one. So if you have other questions, feel free to ask them. Yeah, otherwise we can come back to it after. So I'm gonna take a 180-degree turn to just show you that it's not only about, generative models are not only useful about sampling, drawing samples, but they can also be useful about estimating probabilities. And this can have interesting implication for data reduction methods, which is in complete opposition to the data augmentation we just looked at. Okay, so the context in which we adopted this research direction is for database modeling of multi-scale physics, in particular of closure modeling. So as I said, my expertise is in turbulent combustion. And in turbulent combustion, we usually cannot model the whole system. So we have to filter the system, which give rise to some unclosed terms. In particular, the equation I show on the in the first bullet point is a very important one. That's the transport equation for the species mass fraction. And that's the species mass fraction that determine how reaction rate happen in the system. And when you filter your equation, you do have some unclosed terms that pop up due to the turbulent interaction and because of the turbulent interaction and the chemistry interaction. And so you have to somehow give a good model for what the reaction rate is. So the red term is an unclosed term, the blue term is an unclosed term. For now, I'm going to talk about the red term. And just to see how important that is, this is an example on the right of that I've been working on for a few years. And that's a turbulent ignition event. So you see contours of temperature. On the left, you have an igniter that is injecting some energy. And the difference between the top and the bottom is less than 1% of the energy that we inject. In one case, you do not have ignition, and the other, you do have an ignition. And the drama of turbulent combustion is that everything happens at a small scale and propagates. So if you make a small error there, you can go sideways very quickly. So getting a good model of this unclosed term is really important. And so you could say, oh, that's easy. That's just a regression model that we have to use, and we should be good to go. So what people do is exactly that. They collect data from large numerical simulation that contain billions of data points, typically thousands of snapshots. So you have 10 to the power 12 data points. But the dimension of the data set is usually fairly small in comparison. So it's large but small in comparison. So it's typically on the order of 1000. And that's just the number of species you have plus temperature and pressure. And that is the main problem we're trying to address. How do we handle this large data set? So this typically a normal simulation that we would use to train our model, it would require petabytes of storage. And when you do this, training a model, analyzing the data is just pretty much impossible if you don't have access to a high performance computer. Visualizing is even out of question unless you do you have a parallel system or you do some data reduction. So data reduction is really important there. And you have two ways of doing this. Either you can reduce the dimension of your system, and we have many methods for this. In combustion, we talk about identifying the active manifold, but this is what it means, dimension reduction. Or you can tackle the one that generates the most data, the n, the number of data points. And reducing n now means getting rid of useless data. So people who do simulation of combustion, they don't do this. They don't use billions of data points because it's fun. They do this because combustion happens at a very small scale. And you need so many data points to get the few data points that do matter for you. So in the end, the combustion data set, they usually have useless data and useful data. If we look at our model here, at the simulation I showed earlier, probably what happened next to the igniter is useful. But what happens in this area, for example, would be completely useless for our model. And what we propose is a framework to identify what's useful and what's useless. So what we propose is called uniform in phase space sampling. And out of the capital N data points that we talked about, so trillion of data points, we're going to select much fewer data points, a lot fewer data points, little n, such that the data points are uniformly distributed in phase space. So phase space is the space of the features, so 10 or 100. And the n data points are going to cover the full phase space. So on the right, I show an example of a direct numerical simulation with just 2 dimensions, just so we can look at it. And so this has a 100 million data point, I think. So what that would mean here, it would mean that we would remove a lot of data point in this area, and we consider that we have redundant information because we have a lot of data point very close to each other. But we would not remove a lot of data point, for example, in that area where we have much fewer data points. So we would preserve the rare data point and remove the redundant data. And so the way we're going to do this is using a probability-based sampling. So we are going to estimate the probability of observing data at different locations in feature space. And then using that probability, we are going to formulate an acceptance probability that tells us I should keep the data point or I should discard it. So that acceptance probability is very simply formulated in terms of the probability of observing the data. It's inversely proportional to it. And the proportional constant just dictates how many data points you'll have in your final data set. So on the left, you have an example with a normal distribution. And you're going to try to apply that method there. So you formulate an acceptance probability, and we do this for 2 different final value of little n. So the blue line has a smaller value for little n, the red line has a higher value. So the acceptance probability would be higher if you want more data points. And you can see the probability is lower where you have a lot of data, but it's higher in the tail of the distribution. And in the end, the result that you obtain is the following one. You have fairly uniform distribution in the middle of the domain, except at the tail. At the tail, you don't have a uniform distribution. But if you look at where the tail happened, this is where you have maximal probability. So it's doing the best it can to have a uniform distribution. And at the tail, it's just selecting all the data points. And that's important. I'm not generating new data points. I'm just selecting the ones that I have. Okay. Now we have a different problem. We transform this. We want to estimate that probability efficiently, the probability of observing the data at different locations in feature space. And we have a problem because we have trillion data points, but we also have hundreds of dimension potential. And this is where the generative model can be useful. So generative model are not only GANs, they can also use, so not only adversarial loss, but also likelihood-based loss. For example, normalizing flow or that kind of generative models. So what these models do is that they try to maximize the probability of the point that they are we're generating, which means that internally there is some representation of that probability that's going on, and we are going to use that representation to inform our acceptance probability. And the really interesting thing here is that this normalizing flow can work in extremely large number of dimensions. So people have demonstrated that they can use this for images, so thousands of dimensions. And this is why it's interesting for us. We can use large number of data points easily, and we can use large number of dimensions. And now we're not done, because we have high number of dimensions, but also high number of data points. And you can see there is a circular argument going on. I'm going to train a model to downsample a model to eventually train a model. So ideally, I don't want to use all the data sets to train my probability estimator. So instead, I can train my probability estimator using a subset of the data I'm using. I have at the inputs. And then I use this to have an approximate of the probability. And then I can down select the data the way I explained earlier. So if you do this for the 2D DNS we just looked at earlier, this is what you get. So if little n is 1,000 and little n is 10,000, this is how you downsample the data. So things are fairly uniform in this region. In the n,000, 1,000, it's hard to see, but you do have some sort of uniform distribution, even though there's very few data points. But then here, you oversample the distribution. So what's going on? You don't have the information about this area is an area of low probability. You don't have enough information there. So the model here underestimated the probability. And every time it saw a data point, it said, I need to keep this. This is very important. So this is the consequence of having used a subset of your data set. You did not have enough data in this location to have a good representation of the probability. So we try a bunch of things to improve this. And then we realize that that new distribution of data is an image of the error you're making in your probability estimate. So if you learn the distribution of this that you just generated, you can correct your initial estimation, and now you can redo the sampling. And this is what you get when you do this. So at the cost of doing the procedure twice, you now do get an almost perfectly uniform distribution everywhere, even in low probability regions. Okay, so this method is you can compare it to what people usually do, and you can see why this is important. So when people usually take a DNS data and then train a model, they do a random sampling. They just select randomly data points, then train their model. But you can see that for combustion application, most of the information is going to be lost if you do this. And so this is really what motivated why we had to do this step. We did try simpler method where we cluster the data and then we select uniformly from this cluster. So that's a stratified sampling approach. And this stratified sampling does improve things, but you're really at the mercy of the size of the cluster, which is an issue there, because then you're going to typically sample less in low probability regions. And so this is how our method compares to these two approaches. Okay. And so now the same slide as before. Where do we go from there? Where is that useful? What we can do with this is a data efficient way of learning from it. So we did try in the paper to learn the closure term using this subsample data set. And the comparison we're making is what happens when you use that downsample data sets with a given number of data points compared to other downsampling approaches. And so what I plot here is the error we're making for the closure term versus the sampling probability. And if you remember, that sampling probability is just an image of the actual probability of the data. So high value of the sampling probability means low probability data. Low value means high probability data. And so if you use our method for this, we do outperform the other downsampling method, which is just because we have information where the other don't. But also, we do reduce the variance in our model outputs. So if I redo the sampling multiple times and I use random sampling, I can be very lucky or not. And so usually you want to do your training multiple times to reduce the variance in the output. Same for the stratified sampling. There's always this element of randomness. But in our method, it's extremely consistent all the way through. Even if there is this element of randomness, we did compress it because we are always trying to represent uniformly the data. Okay, and another application we're working on is to scale up to much larger dimensions. We have gone to 18 dimensions to do this. And the reason why that is useful is that now we can represent our combustion data sets in a reduced manner. We can look at different data points that characterize a very large scale simulation. And so instead of trying to, so the typical application here is that you may want to calibrate a model that uses the data from this large simulation. For example, in the paper here, what we did try to do is to make a reduced chemistry using fine chemistry, using a non-reduced chemistry. And so we do a simulation with the non-reduced chemistry. We look at what happens in the domain. And then at those locations, we're trying to match what happens in that flame with our reduced chemistry. That's why we have a robust model that works in most of the domain.
Can I ask a question, Malik?
Yeah.
Can you comment on a little bit on the computational cost of your downsampling strategy against the random sampling? I guess since you need to like follow the algorithm, which seems a little bit complicated, like how does that compare in terms of the cost?
So I think I have something around this. Okay. So
sorry, later your clock, sorry.
No, it's good. I mean, I was basically done. I just had a few other slides to about this. So essentially you have 3 steps that are expensive. You have the estimation of the probability, then you have the evaluation of the probability. So what I did not say is that every time you when you estimate the probability, it's fairly cheap actually, but then for each data point you have to assign a probability there. And that evaluation there is actually a bit expensive, especially if you have billions of data points. So that evaluation step actually scales really well. You can use multiple processors to do this because it's just embarrassingly parallel. The estimation of the probability is fairly cheap. So it's on the order of, for 10 dimensions for our DNS, it's on the order of like 10 minutes because we use a small number of data points. And then we do this 2 times to handle the low probability. The catch here is that you cannot go to a very, very small, you cannot learn your probability with a very small number of data points. There is a limit there, especially in high dimension. So we did demonstrate it works in 10, 20 dimension with maybe a 10-minute training time. But if you are trying to reduce this more, you're going to have trouble. So we have a discussion in the paper about what's the limit there. Yeah, so it is more expensive. So this basically dominates everything. So it's more expensive, but compared to training, doing multiple runs of the random sampling, for example, it's almost negligible at this point.
I see. Thank you.
Yeah. Yeah, and I was basically done essentially. So let me see if I can. Yeah, I was basically done at this point. So yeah, I essentially tried to give you an overview of where this generative model can be used, and hopefully it applies to your domain expertise. And yeah, I just thank my funding agency that fund us for this and my collaborators. And yeah, if you have further questions, I'd be happy to take them.
All right, thank you very much, Malik. Very interesting talk. Are there any questions? I was actually wondering, so this generative models, one of the problems with rare extreme events is that you just don't have enough samples from that regime. And then wondering if you can use this to generate samples without, running your model for a very long time and getting.
Yeah, so we did look at this. I have a conflicted opinion about this. So we did try this on a simple problem, the KS equation, and we tried to generate extreme events by only looking at data that were not extreme. And essentially, the way we define extreme events is looking at that observable value. So you pass a different value for the observable, and then you inject the small scale the same way you would inject the small scale on the high probability data. On the KS equation, it pains me to do this, but it did really well. And I don't like this very much because it's an extrapolation problem. And I think it's because the small scale may be the same, at the low probability and the high probability, the way I defined it. But this is a dangerous problem. This is a dangerous slope, of course. Like generating data that using a data set that is not representative of what you want to generate is very dangerous. So the reason why it worked is because somehow it was a little bit, it was representative of the data that I was trying to generate. So in that case, it works. I don't expect this to work all the time, but I do expect this to work when you have some sort of scale similarity the same way that would be going on.
I think it might have to back that the KS has an inertial manifold where small scales are a function of the large scales. So kind of you're discovering that function.
Right. That's probably what's going on there. And yeah, so I think maybe this would be useful for where we have fluid problem as well, since even though it doesn't have necessarily an inertial manifold, we do have the same behavior where the small scale look the same. But yeah, it seems that we have this separation between, yeah, it does capture this separation where you're trying to capture this observable that is extreme, and through the content loss, you force the field to match that extreme observation plus small scale information that is coherent with low probability. Yeah, I just want to add that for the paper I mentioned about the relevant probability, our goal was not to improve the variance estimate. Our goal was to diagnose why is it that we don't get a variance estimate. So maybe I can touch about this. That would be probably useful. Yeah, let me see if I can. Okay. Yeah, so that's what we talked about. So okay. The algorithm we're looking at is this genealogical adaptive multi-level splitting. And so, as I said, you do intermittently, you do a selection step where you replicate simulation that are headed to other events. And that selection step requires you to perturb the simulation. And what we found is that on some cases, this works with random perturbation, but on other, it does not. And our hypothesis was, what happens if we do a very good estimate of this perturbation? What happens if we do perturbations that are coherent with the attractor of the system? And the way really to test this is to train a generative model to learn how to do this perturbation right. So that's where we use this. And so you can see what happens. I don't know if you see that screen, but yeah, for the Lorentz statistics case, for example, you don't have a lot of spatial variation in your domain. And so it's very easy to use just random perturbation. But for the KS case, we had a lot of issue. And yeah, so when you use random cloning, if this is the parent realization, the black line, and the blue line is the random clones, this is what the GAN would generate. So things that are smooth, even though they are clones and consistent with the energy of the observable, they are still spatially coherent. And we did manage to get some variance reduction. So without using this, we were getting almost no variance reduction. So this is the blue dashed line that we get using random cloning, and the solid blue line is what we get using the GAN-based method. So we did get more variance reduction, but it's not doable in general. Like you would need to train, it's very expensive to train that model. And it worked probably for the wrong reason, but at least it tells us this is important. You cannot just do random cloning. This was more to diagnose what was the reason. Yeah.
Right. Okay. Thanks. Other questions? If there are no other questions, I'd like to thank Malik one more time. Very interesting talk. And we'll see you all in 2 weeks.